Okay, so this is our last topic, IP addressing. I'm going to try and keep it as simple as I can. I want you to really just understand some key concepts. There's a lot of material here. We'll try and get through as much of it as we can, but I want you to just understand some of the fundamentals. And so we're going to talk about some of the base IP or IP address terminology. We're going to talk about this notion or this idea of the hierarchical IP addressing scheme and why it exists and how it's used. We'll talk about different IP address types. And then we'll talk about network address translation, which is an important thing for any network. For you to go from a private or a private network inside your home to a public and communicate with a public server, there needs to be a process for your address to be public. And so, or for you to have a public address. And that's what network address translation is about. And then we'll talk about the newest version of the Internet Protocol addresses, or IPv6. Everything we talk about up until here will be what's called IPv4. Okay. So let's talk about some of the terminology. So an octet, okay, is the same as a byte, and it's made up of 8 bits. So we talked about this a little bit last week, right? So you have in binary 8 bits. Each bit is either a 0 or a 1. When you have 8 of them together, that's called a byte. 4 of them is called a nibble. We're not going to talk about the nibble here, but 8 of them is called a byte. But that same byte is called an octet. Okay, because it's 8 bits. 8 bits, octet, byte. Okay, they're synonyms, they're synonymous. The network address is, you can think about the address being comprised of 2 pieces, a network address and a host address. So then the network address is a portion of the address, and we'll talk about how that address is built up, but the network address is the portion of the address that refers to a network, and the host address is the portion of the network that's, or a portion of the address that's defining the actual host. So think about your home address, for example. If you live on Cedar Drive, let's say 1515 Cedar Drive, okay, your neighborhood address or your network address would be Cedar Drive. But there are a lot of different homes on Cedar Drive. So your host address or your home address is 1515 Cedar Drive. So think about it like that. You've got a network address component and a host address component. And then there is the notion of broadcasting. And I think we talked about this as well last time, but I can send information to a single host, right? Unicast we talked about, or I can do a broadcast. In other words, I can send information to all of the hosts in that particular network. Okay, and there's a specific way of designating that, which we'll talk about. But if I wanted to send flyers to everybody on Cedar Avenue, I could just give it to somebody and say, okay, can you drop these off to every house on Cedar Avenue? And they would do it. I don't need to specify any particular address. Okay. So these are some of the terms that we'll be using as we go through IP addressing. So an IP address, which you're going to most often see look like this, 54.164.151.235. Okay, so when I look at that address, this is an IP address here. It consists of 32 bits. Okay, how do I know that? Because each of these is actually a byte or 8 bits. Okay, so if each of these is 8 bits, that's 8 and 8 16, and another 8 is 24, and another 8 is 32. So each IP address consists of 32 bits, or you can think of it as 4 bytes or 4 octets. And sometimes you need to interchange between the two. That's why it's important to understand whether you're talking about you need to use the bits or you need to use the bytes. Okay. Now, this IP address is structured, or sometimes we call it hierarchical, in order to make routing possible. And by hierarchical, we mean it contains a network component as well as a host component, like we talked about. Okay, same as your home address. It's got a street and a number. So when you look at an IP address, you're going to have some portion of it here, in this case, and the number of bits or bytes or octets that are the network portion and the host portion, they're going to vary, and we'll talk about that. But there's going to be one portion here that defines the network. And then once I'm on this network, this is the specific host that I'm addressing. So in other words, I could have another IP address, 154.102.51.235. So although the host address is the same, 51.235, the network address that I define is different. So it's going to go to a completely different home. It's just like if I have a street address, I have 15 Cedar Drive, but I have 15 Maple Drive, and I have 15 Willow Drive. So I can have the same number on each different street, but to uniquely get to one address, I need to specify both. All right. So when the internet was created, what people realize is that you're going to have different size networks, right? So there are going to be some networks which are huge, right? That are going to have lots of different machines on them, like the internet itself, okay? And then you're going to have other networks which are smaller, so your home network, then you can have networks which are kind of medium size. So let's say bigger companies, okay? So they're going to be small, medium, and large networks. Now, if I assign large networks, okay, if I create only large networks, then I'm going to quickly run out of networks. I'm not going to have enough IDs to define all of these different hosts that exist. Okay, so they created 5 different classes. Okay, we're just going to talk about these first 3, but they created 5 different classes, and we'll just focus on class A, B, and C. And the difference between class A, B, and C is the size of the network and the number of hosts that are allowed on that network as a result. Because remember, in total, you have 32 bits that you can use to define both the network and the host ID. So you can imagine that this has a minimum number and a maximum number with 32 bits. Okay. So with class A, we use the first octet to define the network ID, but the first bit is always going to be 0. For the class B address, we're going to use the first 2 octets to define the network ID, and we're going to set the first bit to 1, second bit to 0. Then for class C, we're going to set the first bit to 1, the second bit to 1, the third bit to 0, but we're going to use the first 3 octets to define the network. And the remaining octets, in each case, define the hosts. All right, so what does that mean? That's a little bit theoretical, a little bit maybe not so obvious about what that means, but let's look at what that means. Okay, let's look at the class A address or addresses. Okay, so the first octet is the network ID, and then the remaining 3 octets are the hosts. We know that the first bit is always going to be 0 here. Okay, so if the first bit is 0, how many bits are left? Remember, 1 octet, 1 byte has 8 bits. I'm setting the first bit to 0. So how many bits are left? We're going to have 8 minus the 1. There's 7 bits left because the first bit is reserved as 0. So if I have a binary number with 7 bits, what's the total number of numbers that I can create? Well, the total number of numbers I can create is 2 to the power 7. So I create 2 to the power 7, or 128 different numbers out of those 7 bits. Or 2 to the 7, 128 combinations of 1s and 0s if the leading 0 is reserved. So that means there are 128 Class A networks. So you can imagine these are reserved for very, very big networks that are going to have a lot of hosts. So if there are 128 networks, how many hosts can I have on each network? Well, there are 8 IPs here, and 8 IPs here, and 8 IPs, or sorry, bits, not IPs. 8 bits, and 8 bits, and 8 bits. That's 24 bits. So if I have 24 bits, how many different combinations of 1 and 0 can I have? Or how many different numbers can I have with those 3 bytes? It's going to be 2 to the power of the number of bits that are there, which is 24. That's going to be over 16 million. So for each of the 128 networks, I can have 16 million, just over 16 million hosts on each of those networks. Okay. Now, just one thing to note that 0 is reserved. We're gonna subtract that. You know, I said 128. 0 is reserved, and 127 is reserved. So for Class A, the network IDs are going to go from 1 to 126 inclusive. That's going to be 126. Although you can say 128 can be created, we're actually only creating 126 because 0 is reserved and 127 is reserved. All right, so Class A address, more hosts, 16 million hosts per network, and smaller number of networks, 128 networks, or sorry, 126 networks. Okay. And the other thing to note, and this is right now, it's not critical well, it's not a critical issue, but it'll come into play, that there are always some number of IP addresses that are reserved. Usually it's 2, the first and the last. The first is for the entire network, and the last is to broadcast. So you always subtract 2. So although it's a 16,777,214, it's actually 212. Okay, remember we talked about a broadcast approach. So that last address is used to when I want to broadcast. So no host can take that IP. So this is the Class A networking scheme or IP addressing scheme. When we go to Class B, and again, the only difference between Class A, Class B, and Class C is the size of the network and the number of hosts, sorry, the number of networks and the number of hosts per network. So if I look at a Class B network, now I've got 8 and 8, so that's 16 bits, but 2 of them, remember the first 2 bits were reserved for, they're set to 1 and 0. Okay. So it means that it's not 16, but I have 14 bits. So how many networks can I create? I can create 2 to the power of 14, or just over 16,000 networks. So for each of these networks, okay, how many hosts can I create? Well, I've got, again, 16 bits. So I do 2 to the 16, and it gives me 65,000, just over 65,000 hosts, minus those same 2 reserved addresses. So for each network, I can create over 65,000 hosts. And if you look at the networks themselves, the first 2 bits are always 0. So the smallest network is when I set them all to 0, which is the number 128. And the biggest network, or the largest number, is when I set them all to 1, which is the number 191. And we talked about binary to decimal conversion last week. So this number is 191, this number is 128. So Class B networks, the network addresses start with 128 all the way through 199. So if I see a network that starts with 15 dot something, that tells me it's a Class A network. If I see a network that starts with 120 dot something, that tells me it's a Class A network. If I see a network that starts with 128 dot something, that's a Class B network. 180 dot something, that's a Class B network. So let's go back and look at my IP. This is one, it starts with 108. Okay, so if we go back to here, 108 is a, 108 is going to be a Class A network. So my external IP is part of a Class A network. It's kind of part of a big network. Okay. If I go to Class C, this time I've got 3 bytes, which are reserved for the network address. And the first 3 bits are going to be 110. So I have 8, 8, 8. That's 24 bits, minus these 3, which are reserved, which is 21 bits left. That tells me there are 2 to the 21, or 2 million, more than 2 million networks I can create. So if I want really small networks, I can create 2 million of them, or there are 2 million available Class C networks. How many hosts per network? So again, these are going to be small networks. I can have 254 hosts because I have 8 bits. So 2 to the 8 is 254. Oh, sorry, it should be 256. And I'm going to subtract the 2 reserved, which is going to give me 254. So if I look at the network address, the smallest is when all these are 0. And in decimal, that's 192. And the biggest is going to be when these are all 1s. That's going to be 223. So Class C networks start at 192 and go to 223. So Class A networks start with 120, it should be 1 to 126. Okay, you can have 128 networks and more than 16 million available hosts. A Class B network starts between 128 to 191, and you can create more than 16,000 networks, and each network can have more than 65,000 hosts. And Class C can have 192 to 223, more than 2 million networks, and 256 IPs per network. Now remember, this was all created to segment IPs, to segment the internet, so that people wouldn't be stepping over each other's toes. So you can apply for a Class A network, a Class B network, a Class C network. But that was the whole point of doing this, to segment them out so that we can have all of these different networks and people can communicate with each other and have their own networks and then go from one network to the other. Okay. So just to look at it a different way, class A, B, and C, this is what the IPs start with. And this is how you'd see the network and hosts broken up. Okay. So class A, fewest networks, most hosts per network. Here you have the most networks and the fewest hosts per network. Big networks, lots of hosts. Small networks, few hosts. And this is, now, the other thing to keep in mind is that there's this notion, you heard me mention it, this notion of a public IP and a private IP, okay? When you're inside a network, in a home, in an office, inside that unit, or inside that organization, or inside that network, you're going to have only private IPs. That means those IPs cannot talk to other IPs in another network. It doesn't matter, in fact, what your private IP is, as long as all of the devices within your private network start with the same network ID, right? So in my case, all the devices start with 192.168.1 something. Okay. Your public IP starts with 2603. I would be interested to see that because you can't have anything higher than 255. It might be an IPv6. We'll look at that in a second. It might be an IPv6 that you're saying. If I do this, well, we'll come to IPv6 in a minute. But you remember we said IP addresses have 4 octets, and each octet, where is it? Yeah, that's IPv6. You're looking at IPv6. We're going to come to that in a minute. So IPv4 has to look like this, where the highest number in any one of these bytes is going to be 255. Okay. All right. So the private IP addresses are for private networks. They're called either private IPs or non-routable IPs, because I can't route from my home IP to your IP, your home IP. Okay. So that's where this the standard, this RFC 1918 standard comes into play. So this defines what you should use as private IPs. So you will never find public IPs with these addresses. So class A, anything that starts with 10 is a private IP. In other words, anything that starts with 10 cannot be a public IP. Anything between 172.16 to 172.31 cannot be a public IP. Anything that starts from 192.168, that starts with 192.168 cannot be a public IP. So those are reserved for you to use inside your offices or homes and their private IPs. Okay. So you have class A, class B, and class C private IP addresses. And again, you're going to assign it to one of these classes based on how big your network is. If I have a huge office, maybe I'm going to use a class B private network. If I have a small office, or a home, I'm going to use a class C, which is what I'm using. I am currently on a non-routable IP. There is no IP in the world that can say, go to 192.168.1.78 and find my computer. It's impossible because it's a non-routable IP. It's a private IP. Okay. In order for me to get information or to communicate with a public server, I need to have a public IP. So how do I get a public IP? So this is what's called NAT or natting, network address translation. Okay, so what happens is you're going to have a device, a NAT device, and in my case, it's the router, and in most of your cases, it's going to be the router as well. And what it does is it manages a mapping between your inside IP and your outside IP. So it basically will advertise an outside IP and say, okay, my outside IP, in my case, it's going to be this 108.18.229, okay, is going to be my source IP. So the source IP for this thing is going to be the 108 dot something IP. So it's going to, because I can't advertise my 192.168 IP, it's an internal non-routable IP. Nobody will pay attention to that. So I have to advertise a public IP, which I get from Verizon. And that's what the IP protocol puts as part of its header as the source IP. And it sends this packet using that IP to this web server. The web server sends the information back to that 108 IP. Now that comes here. Now this thing uses natting to say, okay, and to maintain all of that information and say, okay, that request, I know I'd sent it, and it goes to the inside IP of 10.0.0.1 or the inside IP of 10.0.0.2 or 0.3 or 0.4. So this is maintaining another lookup table between who's sending these packets and receiving them. So network address translation, or NAT, or natting, very, very important concept. And that's how you go from your inside IP to your outside IP. So this web server has no idea about your specific IP. All it knows is it's talking to this NAT device. So the advantages and disadvantages of NAT, you can't see the internal structure. So like I said, this web server or anybody else can't get access to see what your network looks like. It makes it now possible to have unlimited number of small networks, right? Because I can duplicate these IPs, because my private IP and your private IP, my private network and your private network can have exactly the same IP address ranges, but because they're non-routable, I can overlap between your office and my office, or your home and my home. It's not going to matter. So now I can have a essentially infinite number of IP addresses, private. Okay. The disadvantages are, your IP address is going to change. Like you saw, it's a little bit complex to go between the two. And then you've got some delay to be able to switch between the two, but that doesn't really affect us a whole lot. So there are far more advantages to natting than disadvantages, and it makes it possible for us to have all these home networks and private office networks. Now, you may be wondering, well, how does the NAT work? What does it do? Well, it uses something called port address translation, okay, which is one of the most common types of network address translation. Essentially, what it's doing is it's maintaining a table and mapping your requests by port number. So if you send a request from 10.6.1.2, okay, it's going to use this port, okay, and it's going to send that, and when it comes back on that port, it's going to know that that's destined for this particular IP. Or if it comes in on this port, then it's going to send it out on that port, and anything coming back on that port is destined for that IP. So it's using port numbers as a proxy for your IP, but it's still doing that network address translation, because you can see here 10.6.1.2, 10.6.1.6, but they both translate to 171.69.68.10. The IP is the same. The outside IP is the same. What's different is the port. You can broadcast on layer 2, which is the MAC address, and you can broadcast on layer 3, which is the IP address. If you're broadcasting on layer 2, which is the MAC address, you're going to use this, all Fs. And for the IPs, you're going to use all ones, 255, okay, which is right here. You're going to broadcast on 255, 255, 255. Okay. We talked about the ARP already. We talked about DHCP, which is, so the ARP maps your MAC addresses to IP addresses, and DHCP gets you a unique IP inside your network so that you don't have duplicate IPs on any network. So remember, you cannot have duplicate IPs ever, except if they're on private networks, but then they're not duplicate IPs because their network ID is going to be different. Okay, you can have a unicast address, which we again covered last week, which is going to send it to a single unique host. Okay, and then you can have multicast, which is to multiple IP addresses, and then broadcast, which is to everybody. Okay, let's quickly finish up with IPv6. So we're starting to, with all the devices that are out there, your thermostats have IPs, your fridges have IPs, your cameras have IPs. Soon you're going to embed chips in your brain and they're going to have IPs, and everything has an IP. So there is now a new standard that's being put forward, which is IPv6. We're not fully implemented there yet. Many companies don't use it, but the idea here is to just expand the number of available IPs. You can see this table, which is already old. It's from 2010, 11 years ago, and it's showing the available IPv4 address space available. So yellow is already allocated, black is available, not a lot left. Okay, so with IPv4, there are 4 bytes or 32 bits, which is equal to, in total, just over 4 million IP addresses. But when we've used up all those 4 million IP addresses, what are we going to do? That's what IPv6 is meant to handle. Okay. So IPv6 is, instead of 32 bits long, it's 128 bits long. So if you do 2 to the power of 128, this is the number you come up with. And if you want to know how to say it, you need decilong. All right, so right now we're in the 4 million range. By using IPv6, we introduce orders of magnitude more IP addresses. Okay, and some of the advantages with IPv6 is that the routing becomes more efficient. You don't need to do broadcasting. Your network configuration becomes simpler because now you can assign an IP address to every device. You don't need to do NATing anymore. So, the basic problem that IPv6 is meant to solve is how do we increase the number of IPs? But it's more complex to read, and process. So you have this IPv4, and then you had on Slack, you were showing me your IP. This is what your IP looks like. So what's showing up in your browser is an IPv6. So everybody has an IPv6, not everybody. Many companies already implemented this, so you'll have both IPv4 and IPv6. And then there's ways that you can create short forms. So for example, if you have a bunch of zeros, you can shorten it by just replacing them with colons, okay? But you can't do that if you have multiple sets of zeros. You can only remove the 0 once, okay? So, there's different ways to do that. So in this case, if I have multiple sets of zeros, the first set of 0, I would just make it a 0. And then the other set of 0, I can remove them all and just replace it with a colon. Okay. Or I can remove leading zeros. So instead of putting all these leading zeros, it would just look like that: 2001, 1, 2, 3, 4, 5, 6, 7. Okay. But this is something that shouldn't necessarily be top of mind. It's not going to come up right away, but just keep in mind there is such a thing as IPv6, and it's used to expand the address pool.